In this lecture we are going to find the arc length of a curve. So arc length of a curve, arc length of a curve. So for example, let's look at a situation. So where you have a graph. So this is your graph. You can start at a point. So let's say you can start at the point A and then ends at the point B. So we normally call this is the x0 and this is x n. What we normally do is we're going to divide this into sub-intervals. Just to make the calculation easier, we normally divide this into equal parts, but that's not necessary. So let's say we can divide into x1, x2, x3 like that. So it's going to go with x1, x2, x3, and then in general you have x k minus 1 and xk. So we're going to continue like that, and then you're going to get x n minus 1. So so for example, if you look at a general situation, so this is the xk and xk minus 1 and xk sub-interval. So what we're trying to do, so these are the corresponding points on the curve. So what we're going to do, instead of the curve length, we're going to find the this length. So we're going to approximate the curve length by this secant line length. So we're going to connect these two and connect those two, so like that. So we're gonna connect these, and we're gonna approximate the length by length of these curves. These are straight lines. So so if you kind of exaggerate the situation at this point, so this is how it looks like. So so what's gonna happen is yeah, actually, so what's the curve? So we're gonna say y equal fx. So that's the general curve. Only thing is this should be differentiable because we need to find the derivative. So if you have a differentiable curve, you can do that. And even there are certain situations where you can consider several non-differentiable functions as well. So you're gonna kind of split at the discontinuity. But those are like extreme situations. So let's see what's gonna happen here. So if I exaggerate this, what's gonna happen? So this is your curve, and then those are the two points that we were talking about. So so that is the x k minus 1. This is xk, and then what we're gonna do is we're gonna look at the secant line. So what we do, we're gonna consider the triangle, this triangle. So let's assume that this gap is delta x. So I'm going to call this is the delta x, this gap. So if this gap is delta x, this is delta y, and then I'm going to call this length is delta L. So we're gonna and then this is the delta S. So what we're trying to do, we're going to approximate this delta S length by, so we're going to say, okay, delta S is approximately equal to delta S, and this is a valid argument when delta x is small. Okay, so so is a valid argument when delta x is small. That means when delta x goes to 0. So what we're trying to do and how to do that, that means we're going to consider a lot of cuts. So that means if you cut into n sub-intervals, so we have n sub-intervals, when n goes to infinity. So that's kind of how we're gonna approach this situation, because when you're gonna make it smaller and smaller, and you can see that this this length gonna be equal. For example, we can look at a situation where we have like two cuts. So for example, let's look at this situation. So let's see, we have a curve like that. First, let's consider these two situations. So if you have only these 2 points, you can see if you connect the two lines, if you consider the secant line, so this is how it looks like. Okay, so that means you're going to approximate the arc length by this curved length. But let's say you're going to cut this into half. So this is what we have, but we're going to introduce one more cut in the middle. So if you introduce one more cut in the middle, so what's going to happen? So you can see that. So this is, so you introduce extra cut. Now your lines looks like this. So your new lines looks like this. So to be hard to draw, but I'm going to try my best to do it. That's one line. That's the other line, and you can see that compared to the previous approximation, now if you consider the sum, like sum of those two, so if you consider the first one is L1 and the second one is L2 and L3, and this is the actual length that we are looking for, you can see that consider S is approximately equal to L1 situation with S is approximately equals to L2 plus L3. You can see that this situation is much better because the error is very small. Error is very small in this situation. So that's exactly what happens. So when you cut into more and more, the error getting smaller and smaller. So that means when you have more cuts or more sub intervals, then you can see that that's like kind of valid argument that you're gonna get the arc length. So that's exactly what we try to do here. Okay, so let's try to derive the formula here. So what we try to do, we try to approximate the delta S by delta L, that we know, but you can find delta. How to find the delta L? So delta L is, in this situation, delta L is from the Pythagorean identity. If you do delta L squared, which is equals to delta x squared plus delta y squared. So right, and then what you can do is, then we can take the square root. Once you take the square root, then you're gonna get delta L is equals to delta x squared plus delta y squared square root. Now what we can do is, we can make a really nice simplification. I'm going to pull the delta x out. If you pull the delta x out, actually that means delta squared out inside the parenthesis. So that means if you take it out, then you're going to get, so you simply divide by delta x. So you're going to pull out delta x. If you take it out, so you're going to get 1, and that means you simply divide inside by delta x squared. That's what happens. So it's a delta y squared over delta x squared square root, and then you pull out. So I'm going to write it on that side. That's your delta x. That's you pull out. And then so you can rewrite this one like this. So you can say this is simply 1 plus delta y over delta x squared square root delta x. So this is a kind of formula that you're going to get for delta L. So that means, so this is approximate value. So now what you can do is, so you can say that, so this is approximately equals to, this is approximately equals to this one is because that's delta L, this is approximately equal to delta S. So what are you going to do now? We're going to add all of them because that's like a small length. We're going to add the length. That means your total length you can get L is simply you're going to sum over. So it's going to go, let's say there are n parts, so it's going to go y to the nth part. You're going to add such small delta L, so I'm going to call delta L I, the ith part. And then what you want to do, and then also we need to send n to infinity. So this is normally we write this one as we're going to put the limit in front, so we say n goes to infinity, the sum of all those length, so delta li. Now what we can do, we can replace the delta I by this formula. So we're going to go with the ith one. So this is the limit n goes to infinity, n goes to infinity sigma, then I going from 1 to n, and then we have 1 plus delta I gonna say y I, the ith one, so this is the ith one squared square root, and then delta xi, delta xi. So what's gonna happen, this one, you know that this is this has an integral representation. Now there is an argument here, so what's gonna happen, so you can see that when the limit, when n goes to infinity, delta xi goes to 0, so that means you're gonna get delta yi over delta xi. So this is simply gonna be the derivative of the function at that point. So we're gonna simply write as dy over dx at that point. So that means if you want to write a formula, so what's going to happen, so that's the tricky part. So that's delta yi over delta xi simply going to be the derivative at the starting point. Okay, so that means we have a formula now. So this one you can write as an integral representation. It's going to start with the starting point A and the ending point B. So this is simply 1 plus dy over dx squared square root, and the delta xi become dx. So that is the length formula. So we're going to say L. So we derive the formula. So you can see that it's not that difficult to derive the formula. So it's coming from the Pythagorean identity, and then the delta xi over delta yi over delta xi simply become the derivative when delta xi goes to 0. That's you learn in Calc 1. Okay, so this is a Calc 1 result. So the limit of the quotient goes to the derivative. Okay, so we derive the formula. Now what we need to do is to do some examples to see how it works. Okay, so let's look at several different examples. So as the first one, so we're gonna do find the length, find the length of the curve, find the length of the curve y equal 4 square root 2 over 3 x to the 3 halves minus 1 from 0 to let's say 1. These are just numbers, 0 to 1. That's a comma. Okay, so this is the kind of question that you're going to get. So what you need to do is to find the find the dy by dx first, the derivative, and then square it and add it with 1 and take the square root, and then after you get that, so normally what we need to do is we're going to simplify that part first. So we're going to simplify this. So we can write this and we're going to simplify that. So so it's always a good idea to simplify that, and then you take the integrals. So you can see that it won't be that difficult as we think. So let's try to do that. So so let's take the so we have, so the answer, so we have y equal 4 square root 2 over 3 x to the 3 halves minus 1. So that means y prime, the derivative, 4 square root 2 over 3 and 3 halves x to the square root. So if you simplify this a little bit, you can see that a lot of terms get cancelled. So 3 get cancelled and 2 cancel with there are 4, so you can get half of it. So so what's gonna happen is so you're gonna get 2 square root 2x square root, and then what we can do is we can simplify the term, so it is 1 plus dy by dx square, which is equals to 1 plus you're going to square that term, so 2 square root 2x squared, so you're going to get 1 plus 8x. Okay, so you get 1 plus 8x. Now we can write the formula. So so the length is, what are the limits? It's going from 0 to 1. 1 plus dy over dx square root dx. So let's plug in. So if you plug in, so 0 1 1 plus 8x square root dx. So you only need to integrate this one, but this is a very easy integral. If you look at the 4 formulas, you can easily integrate this one, because according to the formula, you have a function and you just need the derivative of the inside function is 8. So that means you can write this one as 1 over 8, and then we have 8 1 plus 8x to the 1/2 dx. So that means your answer going to be, so we have 1 over 8, so this is 1/2, so that means 2/3. So and then 1 plus 8x to the 3/2. So it's 0 1. So we have 1 and a 0. So that's the answer. So you can see, and then what you need to do is you need to plug in the values. But I'm also going to give you a so if you remember the substitution technique, so we can use a substitution technique as well. So if you use a substitution technique, you can use u equal inside function 8x. So and then you can find the du. So this is going to be 8 dx, and then we can use that to so that means so dx is 1 over 8 du. So you can plug in that here, and also you need to calculate the new values. So when we have x equals 0, u equal 1, when you have x equal 1, u equal 9. So you can use those values and you can finish the integral that way as well. So but I'm gonna leave that up to you. So you should get something like this. So that means your integral gonna be 1 over 8 1 to 9 u to the square root du. So that's what you should get, and then if you integrate this one, it is 1 over 8 u to the 3/2 over 3/2 plus 9 1, and you can see that you end up getting the same thing over there. Okay, so that's how you do the integral that way. But here we use the 4 formulas. Okay, so this is simply coming from the 4 formula that we discussed. It's much quicker. Okay, and then if you simplify this one, what's gonna happen here is you can see, so this is 2 and 8, so you can cancel, so you're gonna get 1 over 12, and then let's substitute the values. So if you substitute the values, you plug in 1, it's become 9, so it's a 9 3/2 minus, if you plug in 0, is a 1 3/2, and this is very easy to simplify, so it is 1 over 12. How to simplify 9 3/2? Take the root first. So 1/2 power means a root, so that means 9/2 means 3, and then you cube it, so 27, so you get 27, and this is 1, so that means you're going to get 26 over 12, that means 13 over 6, whatever the unit, to the first power, because it's a length. So you can see that that is the whole problem, and you can do this using the 4 formulas, or you can do using the substitution technique as selecting u equal 1 now. So it's up to you how you want to do it. but the shortcut is the 4 formula. Okay, so this is the first problem, and you can see that those are not that difficult, but we normally what we do is we try to find 1 plus dy over dx squared first, and then you try to plug in there just to make the calculation kind of straightforward. So let's try to do maybe one more example. How about this one? Find the length of the graph. So let's say find the length of the graph of, let's say, fx equal x to the cube over 12 plus 1 over x going from 1 x to the 4. Good. So the answer is so as before, we need to find the derivative. So the derivative of this function is what do you get? So you're gonna get 1 over 4 x squared, and then minus 1 over x squared. That's the derivative. And then what we, after get the derivative, what we normally do is we can do 1 plus f prime x whole thing squared. So we do that. So so that means you can add 1 to this, so it's a 1 plus 1 over 4 squared minus 1 over squared. So let's try to simplify 1 plus. So how to do this? So this is a minus b squared. We know that a minus b squared is a squared minus 2ab plus b squared. So if you use that argument, you're going to square the first one, so you're going to get x to the 4th over 16, and then you multiply the 2 and multiply by negative 2. So when you multiply the 2, you can see the x squared get cancelled, so you're going to get 1 over 4, and multiply by negative 2, so you're going to get 1/2. Okay, so actually negative, so you're going to get negative 1/2. So so you're going to get negative 1/2, and then you're going to get the square of the last term, so that is 1 over x to the 4th. And then you can see that you can simplify this a little bit. So if you simplify this a little bit, so you can combine these two terms together, so you're going to get x to the 4th over 16, negative 1/2 become positive 1/2, plus 1 over x to the 4th. Now if you think of this one, actually there's a really nice simplification. You can see that this is exactly to the square root of this plus the square root of that, and this is going to be the square of this. So there are some nice simplifications going on here. So you can see, just match this with a plus b squared equal a squared plus 2ab plus b squared. So you can see that's exactly what we have. Earlier was minus, now it's a plus. Okay, so we simplify this first. Now we're going to use the formula. So so the length equal starting point is 1 to 4, 1 plus f prime x whole thing square root dx, and then you can see that so we already simplified this, so that we must do the square root. Is simply end up getting x to the 4th plus 1 over x squared after the square root dx, because the square cancel the square root. Now this is a very easy integral, so you can integrate this one, and if you integrate, so you're gonna get x to the cube over 12, and then that's gonna be minus, because x to the negative 2, so that means the 1 over x, and then you're gonna evaluate this at 4 and 1. So let's see how the rest of the calculation works. So let's plug in 4 first. So if you plug in 4, so you're gonna get 64 over 12 minus 1/4, and then minus, if you plug in 1, so if you plug in 1, you're gonna get 1 over 12 minus 1. And then how to simplify this one? So you can see, take the common denominator. So this term you can write as 3 over 12, and then we have negative 1 over 12 here, so it's going to be 4 over 12. So that means you're going to subtract that 4 over 12 from 64 over 12, so that means it's going to be 60 over 12, which is 5, and minus become plus 1. That means you end up getting 6. So answer is 6 unit. So so that's the arc length. Okay, so good. So so as a formula, we can write the formula right now. So let's write the Lindt formula. So what we had was, so what are the conditions that we had? So so we write the formula now. So formula was if f prime is continuous on an interval AB, then the length of the curve, and the length of the curve y equal fx for x in between a and b. That means you can start with a to the b. A is L, which is simply a to b 1 plus f prime x squared square root dx, or in other words a to b 1 plus dy over dx squared square root dx. Okay, so you can use one of those formulas. So what we're going to do is we're going to assume that f prime is continuous. So that means if f prime is not continuous, we cannot use this formula. Okay, we can't use formula. So so in that situation, what we can do is we're gonna see whether we can express this curve not as y equal fx but x equal fy. The other way, we see whether we can solve for x. So sometimes that works. So in so let's see. So let's write that. So if dy over dx is discontinuous, we may use x equal gy instead. Okay, sometimes that may work. So so if you use that one, then your equation gonna be, so let's say so the length formula for x equal gy from y going from c to d, so that's the length formula for the other case. So let's say if g prime x continuous on CD, see the closed interval, okay, CD, then the length of x equal gy for y going from C to D is very similar. So we write L, so now it's going from C to D instead, and then 1 plus dx over dy. So what's we gonna do? You are gonna find the derivative of x with respect to y now. Squared square root. It is not dx anymore, it's a dy problem. So that's gonna be, so, or in other words, C to D 1 plus g prime y square root dx dy. So that's a new formula. Okay, so let's do a problem from that and see why this is important. So example 3, find the length of the curve. Find the length of y equal, let's say, x half 2/3 from x equals 0 to x equal 2. So let's try to kind of do the same thing as we did before. So let's try to find the y prime. So if you find y prime, what do you get? So you get 2/3 x half negative 1/3 times 1/2 by chain rule. So if you simplify this, you end up getting 1/3. 2 get cancelled, so you're gonna get upside down, so it's a 2 over x 1/3 by the negative power, so it can be, so now you can see that, so this is not continuous at, see the first point, see that there's a point inside the interval. At this point it is not continuous, so that means it's not continuous means in this case like not defined. Okay, not defined, so we even don't know what is this. So that means we can use the old formula, so we have to use the new formula. That means you have to write you have to solve for x. So need to use y formula. If it works, okay. So let's see. So so we're gonna do the problem that way. So that means we have y equal what we have, y equal x half 2/3. So what we can do, we're gonna take the opposite power, so we're gonna see y 3/2 is x over 2. So in other words, x equal 2 times y to the 3/2. Now let's try to see what we can do. So then we're gonna get dx over dy. If we do dx over dy, it's a 2 times 3/2 y to the square root. So you can see that works perfect. So in that case, we have 1 plus dx over dy whole thing squared. So this is 1 plus, if you square this, it's going to be 9y. So looks perfect. Okay, and then now what we can do is we can plug into the formula. So the length is so what are the limits? So we need the y limits now. So what are the y limits? When x equals 0, y equals 0. When x equals 4, you're gonna get what do you get for y? Yeah, when x equals 4, you're gonna get y equal 1. When x equals 4, yeah, when x equal to 2, when x equal to y equal 1, not 4. And so, and then 1 plus 9y square root dy. So this is very easy to integrate. So so you're going to multiply and divide by 9, so it is you're going to get 1 over 9, and then you can simply treat this one as x, so it is 2/3 1 plus 9y to the 3/2, and then if you plug in the numbers, you end up getting 2 over 27 10 square root 10 minus 1. Okay, so that is the that's the exact answer for that. So you can see that you cannot do this problem using the x, but you can do this problem using y. Okay, so so this is the kind of what we need to do. So we did 2 problems from x and 1 problem from y, and there's like a small topic here, so I'm going to kind of quickly go through that as well. What we call it arc length formula, or arc length function. Arc length function. So what is arc length function? Is like, let's say you have a curve. So you have a starting point. So let's say you want to find, for some reason, what is the length starting at this point. You know, you're going to find the length of this curve starting at that point for a general point x. So this is x point. So you need to know what is this length. What is this length? Okay, so that's the so s. So this is what we call the arc length function. So what you do is the same thing. So you're going to do you're going to write starting at a, you can write up to a general x. So that means you have a starting value a in the bar there, and then to x. So that's what we call the arc length formula. It's the same thing. So if you have y equal fx, so you can have 1 plus f prime x whole thing squared. It's the same thing, dx, or you can even have dy if you want. So this is what we normally call the arc length function, because you can see that it's a function of x. Okay, so this is a function of x, function of x. So that's why we call this arc length function. So we normally call this arc length function. Okay, so instead of getting a number, you get a function now. So yeah, so that's the kind of things that we need to do. So we can probably do just a yeah, maybe we can do so you can yeah, so let's just do one example from this one in case. So let's say find the arc length function. Find the arc length function for the curve, y equal x squared minus 1 over 8 ln x, taking p naught, the starting point, as 1 1 as the starting point. Okay. Yeah, so I mean there's nothing new here. So so only thing is we can write x, it's not a to b now, a to x, so that's the only difference here. So we can say x prime in this case, derivative prime is, what do you get? So let's say I'm going to start with like fx. So fx is x squared minus 1 over 8 ln x. So that means f prime x equal to x minus 1 over 8x. So 1 plus f prime x whole thing squared equal, what do you get? equal 1 plus 2x minus 1 over 8x whole thing squared. So this is 1 plus 4x squared. You multiply the two. So if you multiply the two, you're gonna get negative 1/4. So you're gonna get negative 1/2 here, and then you square the last one, so 1 over 64x. So this is like a kind of x squared, pretty much similar to what we did before. So there's a cancellation going on here, simplification, not cancellation. So and then you can write this whole thing as, so what do you get if you do that? You're gonna get 4x squared plus 1/2 plus 1 over 64x squared. Actually this is simply 2x plus 1 over 8x. You can see only a sign change now, so negative 1/2 become positive 1/2 squared. Perfect. Now we can write the formula. So the arc length function, arc length function, we're gonna write Sx is simply, we're starting at 1, it says 1 to x, and then we have 1 plus f prime. Okay, now don't write x here because we are using yeah, it's kind of I actually need to go back to and change this one. We normally don't write the same letter, so I prefer to write something else here, so just to avoid the confusion. So we can write like something else as a dummy variable. So let's put t, so use something else. Okay, so don't use the same thing for the dummy variable because this is x, so use something else. Yeah, so I forgot that. Okay, good. So so the same thing going on here as well. Remember we used that idea in the fundamental theorem of calculus, so we something else here. Okay, good. And then we're gonna square, take the square root dt. So you can see that same thing, we have square and square root, so that means it's gonna be 1 over x, 2x plus 1 over 8x only because of the square. And okay, it's not x actually, it's t. I forgot that again. But the variable is t, so x, just a t and a t and a dt. These are very easy integral. So if you integrate, what are you gonna get? So you're gonna get t squared, this is, and then plus 1 over 8, this is 1 over t, that means ln t, and then it's gonna be x and a 1. So let's plug in that. So if you plug in x, you're gonna get x squared plus 1 over 8 ln x minus, plug in 1, so 1 plus 1 over 8 ln 1 is 0, so that means you're gonna get x squared plus 1 over 8 ln x minus 1. So it's kind of interesting how the calculation goes. So this is what we call the arc length function for this one. So that means if you know any other point, so for example, if you know to find the arc length at up to the point x equal 3, you just need to plug in 3 and get the answer. So it's kind of interesting, very interesting. So good, so that's about that, and I would like to do one more example, like a general problem as the final one, just for extra practice. So let's see, so this is the last example of this one, just extra problem. So let's say another problem, find the arc length, find the arc length of the curve, find the arc length of the curve y equal, let's say ln absolute value of cosine x from 0 to pi over 4 maybe. Okay, find the arc length of the curve y equal ln absolute cosine x from 0 to pi over 4. So I mean, just another problem. So let's see how it's gonna work. So we have y equal ln. Actually, from 0 to pi over 4 is cosine is positive, so you really don't need absolute sign. You can just write it like that because it's positive. So then we're gonna go for the derivative. So derivative is, what's the derivative? Cosine. So the cosine goes down, multiply by the derivative of that. That's how we normally do derivative of log. The function goes down and then multiply by the derivative. So this is simply negative tan x. Perfect. And then we do 1 plus f prime x squared. That means 1 plus derivative is this one, so you're going to square, so that means give me tan squared x. So 1 plus tan squared x, according to the formula, this is secant squared x. Remember, this is one of the trig formula. So now we can find the length. So the length is length L, which is 1 to pi over, okay, actually let's write the formula. We know the formula now, so we can write it. And then 1 plus f prime x whole thing squared square root dx. So that means it is 1 to pi over 4 secant squared x square root dx. So this is 1 to pi over 4, the absolute value, but this is positive, so you can just say secant x dx. Secant x, this is one of the formula from the trig integrals. What's the integral of the secant? Anyone know what's the integral of the secant? Integral of the secant is natural log secant x plus tan x. So that's, you need to remember, this is one of the formulas you remember, and you can evaluate at pi over 4 and 1. So let's plug in the values. So ln secant pi over 4 plus tan pi over 4 minus ln secant actually it's not 1. Yeah, I think I made a mistake here, there, and there. So this is 0, it's not 1, it's 0. So it is 0, 0, 0, and 0, and secant 0 plus tan 0. So let's try to find those values. So what are the values? So the values are tan pi over 4 is 1, tan 0 is 0, secant 0 is 1 because the cosine 0 is 1, so this is 1. And the secant pi over 4, we know that the cosine pi over 4 is 1 over square root 2, so that means it's going to be square root 2. So that means we can end up getting ln square root 2 plus 1 here minus ln 1, but ln 1 is 0 again, so that means your answer is ln square root 2 plus 1. So that's what you get. Yeah, so this is like, maybe another example that we can do. So I'm going to give you a extra credit problem, so if you want you can try this and send me. So this is a extra credit problem, so I'm going to say easy. So what is that? So let's say find the length of the curve, y equal ln cosine x from pi over 6 to pi over 4. Okay, so you can do this problem mention me. Yeah, so you can see that this answer is like really kind of beautiful. So I'm gonna call this is a beautiful problem. Okay, so you're gonna see a separate video for that later. Yeah, so thank you. So this is the end of the arc length function. Thank you.